Okay, so just to remind you, this session has been recorded. Today, once again, we'll be discussing the transfer function of frequency domain circuits, series resonance, parallel resonance, and Bohr plots. I don't think we'll be able to cover Bohr plots today, so we will go until 3.4. At the end of this session, we will be able to understand what is resonance, what is the transfer function, and what are filters. All right. Frequency response. When we say frequency response, if you go back to your signal and systems course, do you remember what is a step response? Can anyone tell me what is a step response? Anyone? Can you guys hear me, by the way?
Thanks.
Okay. What is a step response? Anyone? Anyone? You have done step response, impulse response, all of this. You have done it in your signal and systems. I would like to see if someone knows what is a step response. What is it like by definition? Anyone? Can I take some name? Maybe Ong. Ong, do you know what is a step response? Ong Jasheng. Alicia. All right, Luqman. I hope you guys can hear me. I hope. Okay. Let me tell you. As the name says, step response. A response of a system, of some system or of a circuit for a step input. An impulse response is the response of the circuit of the system when the input is an impulse. So response to any particular input is called that particular input's response. In similar way, frequency response is the response to varying the frequency. So if, as you can see here, it is the variation in circuit's behavior with change in signal frequency and may also be considered as a variation of gain and phase with the frequency. Just remember that when we are talking about frequency, we are talking about S domain or J omega domain, and this means we are talking about complex numbers, phasors, and in the phasors we have those gain and the phase. So we will see that the gain and the phase will be changing depending upon the input signal or depending upon the circuit. So basically, the frequency response is when we have a frequency at the input, a sinusoidal or some particular wave. It is a complete description of the sinusoidal steady state behavior of a circuit as a function of frequency. So it is a function of frequency. Frequency response is a function of frequency. All right. So we move to the next slide. So what is the transfer function? You have discussed this before. I think it's already very clear, but transfer function of a circuit is the frequency dependent ratio. So it is already defined here, frequency dependent. So it should be in frequency domain of a phasor output which is Y, an element of voltage or current. So it could be voltage or current or any particular variable in the circuit to a phasor input source voltage or current. So basically we are taking the ratio of the output in frequency domain with the ratio with the input in frequency domain, and normally the input is the source and the output is a particular element in the circuit, and we're talking about its voltage or current. So let's say there's a capacitor here and we're talking about the voltage of the capacitor, or an inductor and we're talking about the inductor of the current of this inductor. All right. So it's a ratio of output and input in frequency domain, and it could normally we're taking the voltage or current here or voltage or current here. Mathematically we can express it like this, that the transfer function is y upon x in frequency domain. This omega shows frequency, and since it's a complex number we can express it in amplitude or gain, or uh, gain and phase. Okay, amplitude and phase. So this is just sort of a recall of, and how do we find it is very easy. First of all, transfer function is a tool to find the frequency response of a circuit. Once again, let me go back to the basic definition. This is the basic definition. So suppose we have the transfer function of this particular system, network, circuit, or whatever. Okay, the advantage is that it is a ratio of output and input. Of course, there is no benefit in knowing the transfer function itself unless we are trying to find the output to a particular input. So the advantage is that if we have the transfer function and we want to find out what will be the input, or what will be the response of this system if we apply a particular input. Does it say that it is 10 sine omega t or 27 cosine 5t? Does it say that? No, it's input, it's output. It doesn't say anything about what input. It could be any input. So the thing is, once we have this, once we have the got stuck, once we have the transfer function, so it's like we know what the system is. Let me take a very simple result. Let's say this is multiply by 2 circuit. Multiply by 2 circuit. So it will be let me just. So it's a multiply by 2 circuit. So whatever input we have here, it will be multiplied by 2. Y will be 2x, right? So basically we know what this system is doing, what this system is like doing to the input, and if you see that this can be written as y upon x equal to 2. What is this 2? This 2 is this transfer function. All right. So basically, once we have the transfer function, we know what the system is doing to that particular input, and we will know the output of the system. Okay. So transfer function is there's a tool to find the frequency response. So response, whenever we talk about response, it means the value at the output of a circuit. Sometimes h omega is also called network function. So just another name. Frequency response is a plot of h omega versus omega with varying omega from 0 to infinity. So it's a plot. It's a plot. On the x-axis is omega, and on the y-axis is h omega, and we will be seeing that it is basically the amplitude and also the angle as well. So we have two plots. We'll see that later in a while. All right. So it is depending. So just like when we talk about f of t or x of t or y of t, y is a function of t, x is a function of t. Here h is a function of omega. So just like sine omega t, we have t on the x-axis and the amplitude is changing with time. Now here we're talking about changing the frequency on the x-axis and changing with frequency. What will happen to the circuit or the response when we change the frequency. Maybe later I'll tell you how is this useful. The idea of transfer function is implicit in the definitions of impedance and admittance to relate voltage. And when we talk about particularly circuits, so now we know that the voltage and the currents are the two variables, and we can relate these two variables in terms of transfer function. So it could be a voltage gain. So this is output and input. It could be a current gain. It's too mixed up. A current gain, output current, upon input current. It could be the transfer impedance. Also, this is just another name to say the transfer function, but if you see the definition is V over I. V over I, remember, is impedance, and similarly I over V is the admittance. So when we look from this side, what impedance are we looking at is basically this one, or what admittance you're looking at is basically this one. So it can have four types. If you see, is output and input, voltage and current, and these can be related that the output voltage over input voltage, output voltage over input current, or output current upon input current, or output current upon input voltage. This is how we can define different ways, right? So nothing to worry about. It could be anything. So as simple as that, like as long as it is output upon input, it can be considered as a transfer function. We need to see which context we are discussing the circuit. All right. So let's take a simple example. For the RC circuit shown here, obtain the transfer function V0 over Vs. So now it's important that you should know what transfer function you're looking at. If you see in the previous circuit, previous one, it has like four different types of transfer function. So if they say find the transfer function, you will be puzzled that, okay, are they asking about VO over VI or IO over II or something like that. So suppose in case it is not mentioned that what transfer function you're looking at, you have to sort of assume, okay, since it is not mentioned, I'm assuming, like for example, for this circuit, suppose this part is not given. Okay, if it's not given, then you have to sort of assume, okay, since it's not given, it looks like Vs is the input and V0 is the output, so I'm considering V0 over Vs as the transfer function. By the way, you see that in the circuit, this is small and but this is capital. What's the difference? What's the difference, guys? Today you guys are a bit sleepy, is it, or something? Time domain and S domain. Yes. Yes, Nazirul, capital letter in frequency domain. Very good, Anshin. Yes, we consider small letters for the time domain, and we take the capital letters for frequency domain. Some differences in terms of amplitude and RMS values, we'll come to that when we discuss later. All right, so we need to find the transfer function of this circuit. We're looking for VO over Vs. What should be the first step? What should be the first step for this particular question? One upon SC. Okay, 1 upon SC. Why is it, Arif? What are we doing actually? I agree with you. What are we doing? Arif has said that it's 1 upon SC. I agree with Arif, but what are we doing actually? S domain, right? Yeah, maybe you mean to say that we are transferring this into frequency domain. Yes. So remember, transfer function is, let me just silence this one. Okay. So we are converting the circuit into frequency domain, and if you've noticed in the previous slides, we're talking about omega. So we are talking about a subset of Laplace, which is, remember, S is sigma plus j omega. So we are just talking about omega in this case. We're not talking the complete response. We're just talking about the frequency response. So we are transferring this circuit into the omega domain. And if you remember, for capacitor, it was 1 upon j omega c, which is 1 upon SC if we consider the whole thing. So good. So the first step is, now you can see that this is in capital and this is also in capital. right? So we're looking for V naught, which is the output voltage in terms of Vs. What is the transfer function? Transfer function is representing the circuit parameters in a way that we just have two variables, the output and the input. In this case, looks very easy if you just apply voltage division. So VO is voltage division on this, so 1 upon j omega c upon R plus 1 upon j omega c times Vs, or V naught upon Vs is okay, let me just put it like this: 1 upon j omega c upon R plus 1 upon j omega c. Is that right? And one good thing about not good thing, the, the input is given here, but remember that in transfer function we want to have it in terms of output and input variables. So I'm not going to put Vs coming from here. We're not putting S spawn S square plus omega square. No, we just keep it as Vs as the source voltage. Okay. So basically it's like this, the transfer function. Am I doing it here? Okay. So the transfer function we just got was V naught over Vs using voltage division will be 1 upon j omega c upon R plus 1 upon j omega c. Any questions so far? Any questions so far, guys? Okay. All right. So this is the transfer function, but we would like to see the transfer function. Remember, transfer function has poles and zeros, so something like that. So one form of a standard form is writing them in 1 plus something, 1 plus something, 1 plus something. So we would like to write them in a way that they are 1 plus something. Either we take this R common or we take 1 upon j omega c common. So I'm taking this 1 upon j omega c common, so that we get rid of the denominator as well. I hope that you will agree that it would be in 1 plus j r c omega, or the better way is to write it j omega rc. Agreed? Is that okay so far? No, sir. No, sir was for what question? Guy, what was the question at that time? Any more question, I think. Okay. So let me know if there's a question, okay? Probably because I'm using two devices, so just like unmute your mic and you can ask. All right. Since we will be looking at particular frequencies later on, so it's not bad to define a frequency that is in terms of the circuit elements. Circuit elements are R and C, and we just define a parameter which takes care of this RC in the in the expression. My handwriting is too good. All right. So I am defining omega naught, which is 1 upon RC. And there's a reason of keeping 1 upon in a way. So it will become 1 upon 1 plus j omega upon omega naught. Right? So far so good? Okay, and remember we are looking at something that makes omega relating the h omega. This is basically h omega. And we cannot have h omega. We'll have h omega as a complex number. So we'll be looking at the magnitude and we'll be looking at the phase of h omega. So if we are looking for the magnitude h omega, remember magnitude is, you know, the Euclidean norm, square root of the x or the real and the imaginary part. So uh, in this case it will be square root of 1 square plus the imaginary part is omega upon omega naught square, right? This is the magnitude. And if you remember the phase, we find the phase using the tan inverse y upon x. And if we look for the phase of this one is like in the numerator is 0 because this is just a constant, and in the denominator it will be tan inverse you know y upon x. So y is this and x is this, so omega upon omega naught, or since this is 0 it will be minus tan inverse omega upon omega naught. Is that okay? This is simple taking magnitude and phase. So if you want to just give it a try, put some number upon for omega and omega naught, you can find that okay, this is how we find the magnitude and phase of an expression. All right. I don't want this. Later on I will delete some more things as well. Can I reduce it somewhere? Okay. So far so good. Any question, anyone? Okay, chat window says nothing. All right. So if we try to plot this, I'm trying to plot the h omega, the magnitude, all right, which is 1 upon square root of 1 plus omega upon omega naught squared. So when omega is 0, what will be the value of h omega? I have to improve my handwriting. No, I don't want this. Subtitles. I'm going to turn it off. Yeah. So when omega is 0, what will be the value of h omega magnitude? What will be the value of this? 1. Very good. So we start with 1. Okay. And actually the idea of having the frequency response is that we start increasing omega and we keep on increasing until infinity. So theoretically, if someone wants to plot the magnitude response, he has to find the values of omega and then keep on plotting. So the next step should be, let's say omega equal 0.01 and 0.02 and 1, 3 and 4 and 5 and 6 and 10 and 20 and so on. So let's keep another value, which is omega equal omega naught. What will be the value of h omega when omega equal omega naught? It will be 1 upon under root 2, right? 1 upon 1 plus 1 square, so somewhere around 0.707. Agreed? So let's take a value omega naught, which is actually 1 upon RC. So the value will be this. So it's like decaying. And if we keep on decaying, we'll see that it comes out to be like this, something like this. And you will agree that we are increasing omega, which is in the denominator. It will keep on decreasing and decreasing and decreasing, and we'll see the response like this. Is it okay? And if we try to plot the phase, so what if omega is 0? What will be the angle if omega is 0? Tan inverse of 0 is 0. Let me make the line a bit higher, because you know it's a negative. So I'm expecting something. So as we go on increasing the frequency, we will be decreasing in negative direction, and at the same value as omega naught. So it's like tan inverse 1. What is tan inverse 1? Tan inverse of 1 is 45. So this value will be 45. By the way, don't worry about how we are doing it. It's just putting the value in this omega and finding numerically. So this is the very basic way to find the frequency response, that we put omega, but practically it is impossible because we are trying to go for infinity. It's impossible. Okay, so at infinity, remember tan inverse of infinity is 90. So the maximum it will go will be until 90. Let me sum it up in a way. Magnitude, phase, don't worry about this. I'll be showing it here. Okay, so this is all what we did in the previous slide, just to discuss in fair way, I would say. So this is like applying voltage division and putting this in standard form. Magnitude is keeping this with having. So if you see that if we keep omega as 0, it will be 1 upon 1, starting with 1. And if omega equal omega naught, it will be 1 here, and 1 plus 1 means 1 upon under root 2. 1 upon root 2 means 0.707 like this. And if you keep on increasing, it will go like this until infinity. At infinity, it will be 0. Similarly, for the phase is minus tan inverse omega upon omega naught, and the plot will be something like this. So far so good. Once again, this is the very basic way to plot the frequency response, but that's not the way we'll be doing it later on. So this is just for basic understanding. All right, before we proceed further, look carefully on the magnitude or the H plot, the one here. Okay, what do you see? Can anyone comment on this particular thing? What is happening when we are increasing the frequency? What is happening when we're increasing the frequency? Anyone? Very simple, it's very obvious. In this particular plot, what is happening when we are increasing the frequency from 0 to infinity? What is happening to the magnitude? It's going to 0. Okay, so initially it's 1. So if I say that if the frequency is 0, the magnitude is 1, right? And as we go on increasing, the magnitude starts to reduce and reduce and reduce and so on. All right. Can I say that if suppose omega is 0 and the magnitude is 1, if we go back to the basic definition of transfer function, which is, I would say y of omega is equal h of omega times x of omega, right? what is the transfer function doing when omega equal to 0? What is, so if we are talking about this system and this is equal to h omega and x and y, what is h omega doing when omega equal to 0? Anyone? This is about basic understanding. That's why I'm asking. This is a very simple thing. We might have seen it so many times, but it is important to understand. Y equal to x, very good. What does it mean? What does it mean? Short circuit. Okay. Okay. Can I say that the system is doing nothing to the input in layman's term? And it is letting the x go past it until the y. The system is letting x to go through it. Right or wrong? Guys, if omega equal to 0 and magnitude is 1, in which case h is 1, so y is equal to x, can I say that h it is letting pass x without any change? True? Okay. And suppose I start increasing the frequency, it is decreasing a bit, and if we go with higher frequencies, it is, so let's say this frequency is suppose 10. What is happening when the frequency is 10? What is happening when the frequency is 10? Is it letting x pass through it? At omega equal to 10, is the system letting the signal x pass through it? Yes or no? Parindra, what do you think? I like your name, Parindra, by the way. Parindra, what do you think? Is the system, when the frequency is 10, is it letting the x pass through it? Yes or no?
I think so. Yeah.
You think that it is letting it pass. Letting it pass means
Oh,
that.
no, no, sir. No, no, sir.
Okay.
It's not letting it pass.
No. Okay. Can I ask why? Why is it no?
Because because the part where the value 10 is, that's where the graph ends. So, yeah.
The value of this will be like very low, right? Very low.
Yeah.
And this means it is almost 0,
Yeah.
right? Okay.
Yeah.
Okay. Let me just redraw this curve, and I suppose I'm able to make it in a way that it looks like this. So let me just erase all the ink from here, and can I choose the different color so that, okay. So I'm able to suppose draw the plot like this. I'm somehow say able to make this curve in a way that it looks like this. So what do you say? What do you see now? Let me ask someone else as well. Get ready, girls from. Okay, Sarania. Is girl or boy? Sarania? Sarania? Can you unmute your mic and let me know what is happening here? Parinda has already given us a hint that at this point it is letting it pass, but at this point it is not letting it go. Can you comment on that? Sarania, are you there? Gan Yi, Gan Yi, Singa Yi. That name comes next. Guys, you have to like. It's already very non-interactive class because of. Okay, Sarani, you're here. Can you comment on? Can you unmute your mic and can you comment just whatever you understand? I can help you. Just start talking and I'll help you out. Can you unmute your mic and start saying something and I'll help you out what we're looking at. Guys, don't be shy, please. Okay. Atika. I'm targeting girls today. Don't be shy, please. The boys have been active actually. Yes, Atika. What do you say?
Letting it pass until at one point.
Okay, very good, very simple. It is letting it pass until one point and after that it is blocking, right? It is letting
Yes.
it pass and after that it is blocking. Okay. Uh, is it blocking the high values of omega or low values of omega? Is it blocking high values of omega or low values of omega? Atika?
Low.
Low. No, is it blocking low or high? Blocking.
What do you mean, sir?
Blocking, like, as we say that this point it is one, letting it pass, and this point they are stopping it. So which frequencies are being blocked and which frequencies are being let go?
High frequency.
High frequency blocked or let go?
High frequency is being blocked.
Oh, very good. Excellent. This is what we needed from this particular plot, that it is allowing the low frequencies to pass and high frequencies to not pass. Does it give you a hint towards a particular type of circuit?
Not sure, sir.
Okay. Anyone want to comment on this thing, that what type of circuit is allowing the low frequencies and not allowing the high frequencies? Okay. They're called low pass filter. Low pass filter, I'm sure you must have at least heard of these filters somewhere. Low pass filter is allowing the low frequencies. Of course, there is deterioration in the amplitude, but to some extent it is allowing. But after that, the amplitude is so small that we can sort of say that they're not allowed to pass through it. Okay, so if we put a signal here and if it has a low frequency, actually the term is actually omega naught. 0.77 is sort of an effective value. So if it is more than omega naught, the frequency, it will appear here with a good enough amplitude. But if it is higher than say omega naught, it will be so small that we will be ignoring it actually. Some that depends on what application we're talking about, but 0.77 is a good number. But some say zero point 0.5, some say 0.8, 0.9, but for this particular example is 0.77 or whatever it is. That's what we call the cutoff frequency. Cutoff or like critical frequency, or a particular frequency that we are interested in, that we want to block. So let's say if we have a signal, we want to do some processing. I'm talking about signal processing now maybe, and we have high frequency noise added to it. So if we apply this particular low pass filter to it, that high frequency will be blocked. That will be blocked and we will receive the original signal. This is what a low pass filter is. Is that okay? So a circuit with and if you see if its omega naught is 0, oh sorry, if omega is 0, what is the shape of the signal? If omega naught is sorry, if omega is 0, what is the shape of the signal? What is the type of the signal? This is basic. Once again, this is important to understand this. This is basic. So I'm repeating my question. If omega is 0, what is the signal type? What is the signal type? I can't hear you. Anyone, please? Okay, let me go to the boys this time. No change. Okay, no change. No change is like not an engineering answer, you know. Okay, no change. Which signal do not change? What type of voltages or current do not change? The boys. Murtaza. I found Murtaza's name in the front. Murtaza. Voltage remain unchanged. What does unchanged voltage mean? I'm talking about this value, this voltage. If I keep a voltage with zero frequency, what is a voltage with zero frequency? What is zero frequency? Guys, this is very basic physics. Okay. When I will say the answer, this will be your answer. Oh, like this, huh? DC, direct current. No, it's not that complicated. Your answer will be oh, right? So if omega is 0, this means it's DC. It's not AC anymore. And if you remember from circuit theory, for DC source or DC circuit, what happens to the capacitor? What happens to the capacitor for DC voltage? Open circuit. Very good. And if it's open circuit, what will be the value of V naught? Vs. Yes, Vs. So isn't this also obvious from here? Or the way I wrote x equal to y, or like y equal to x. So this circuit is your first filter that you have already designed. It's a low pass. Oh, this, see, Mohiman is now saying, oh, so I always love this. Okay, so basically this is your first filter that you have designed. It's a very basic filter. It has just an R and a C, and you apply a voltage. For low voltages, it will allow it to pass. So for, you can, if you forget, you can consider that for low voltages, the capacitor, or like zero voltage, for low frequencies, the capacitor is sort of open circuit and it is maintaining the voltage whatever is input. This is coming from circuit theory. For a zero voltage DC, it 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 reflects same voltage as the source, right? Or in short, this is a circuit that blocks the high frequencies and allows the low frequencies. Is that okay? This is high frequencies all blocked and these are allowed. Is that okay? All right. This should have come yesterday. Okay, so let's take a look at another circuit, and if we look at it from the perspective from the end that we just discussed. In the previous circuit was a capacitor, and here we have an inductor. Okay, what happens to inductor for DC? What happens to inductor 8 for DC circuits? Short circuit, short circuit. Very good, very good. Alhamdulillah. So basically this will be like this. Short circuit. What will be V naught? What will be V naught? 0. Very good. So for sources with DC or frequencies are low, they become short circuit. So V naught is equal to 0. What are we expecting to have this circuit working as? The previous one was allowing the low frequencies. This one is giving a 0 output for low frequencies, right? So what type of circuit we are going to make, or we will be we are understanding in this particular circuit? Let me draw it again. For low frequencies, this was like open circuit. Okay, and this means that this voltage was appearing here. Here for low frequencies, it is 0. In this one, for high frequencies, the voltage was 0. Here for low frequencies, the voltage is 0. What type of circuit are we looking at? If you try to maybe relate them. Yes, it will be a high pass filter. So you can see that low frequencies are blocked. Output is 0. And of course, high frequency will be there. So we will be looking at, I don't need all this. All right, so just follow the previous technique. Okay, so using again VDR, we can say that VO upon VS is equal to, of course, it will be like J omega L and R plus J omega L, right? Okay, and if we want to keep it in standard form, I'm taking this R common, so it's J omega L upon R and 1 plus J omega L upon R. And just like previous one, if I keep omega naught equal, so I'm trying to bring omega naught is in the ratio for omega, so R upon L. And this is just to make things easier later on for plotting and everything. So it will become J omega upon omega naught upon 1 plus J omega upon omega naught. This is the standard form. We normally call it standard form. All right. Standard form should be coming here. So magnitude, what will be the magnitude of this? The magnitude of the numerator is omega upon omega naught. And the magnitude of the denominator is very simply just like last time, 1 plus omega upon omega naught square. All right. Is it okay so far? Anyone not following? Once again, we applied VDR for this this voltage is V naught upon Vs equal this impedance upon the sum of impedances, this, and then we did this in standard form. So I'm taking this R common is 1 plus J omega L upon R and J omega L upon R with omega naught equal R upon L. So this will be in reciprocal, so j omega upon omega naught and 1 plus j omega upon omega naught. And if we want to find the magnitude, we can do it both in numerator and denominator. This is just the imaginary part, so is omega upon omega naught. It was actually 0 plus j omega upon omega naught. If you put like this, 0 plus omega upon omega naught square, so this will go and we'll get omega upon omega naught in the numerator. Okay, I don't want this here, go away. All right, and the phase will be okay. If we just look at the plot for this one, just like before, for omega is 0, so this is 0 and this is 0, so you can see that it is 0, and as we keep on increasing omega, it will increase for omega naught, or for omega equal omega naught, for omega equal, so it will be like 1 plus 1 and 1, so it's like 1 upon under root 2. Okay, so 0.707, so this is here like this. And if we keep on increasing, if we go for omega infinity, of course it will be infinity upon infinity. It's like kind of 1, because it's like bigger number, it should be 1. All right, so this is for the magnitude. And for phase, once again look at this expression. Maybe this expression, it's like j omega upon omega naught. It's just the imaginary. If you remember, if it's just j, the angle is 90, so it will be angle 90, and the denominator is tan inverse, but it comes up is like tan inverse omega upon omega naught. Is that okay? And for this particular case, the phase plot will be this, and it will be a high pass filter. Normally we are more interested in the magnitude plot compared to the phase plot, but anyways, this is also important for some phase difference and how much difference it will create. It will be a high pass filter. All right, and in like my good handwriting, so it's all the same, just to make things clear. Any question? Any question before we proceed? Can we take a break here, 5 minutes? I'm going to pray and we'll meet at 5:09, right? Take a break. I'm pausing the recording. How to pause the recording? Can you pause? Only can stop. Okay, I'm stopping the recording. I'll start again, inshallah.